In the last video, we did a hypothesis test on a population in which we knew the population's standard deviation, normally signified by sigma. Now, we usually don't know that, so that's usually something that we don't know. So we're, in this video, going to do the exact same example, but we're going to assume that we don't know this value. And then let's see what happens differently. Okay, so let's go back to the exact same information we had before. We had a population. They thought their mean age was 30, and you say, no, it's not. And so you set a hypothesis, a null hypothesis, a hypothesis of no difference, that the population's mean is 30. And so you set the alternative hypothesis to say, no, the population's mean is not 30. So we're going to try to reject this in order to accept this, right? So we collect some data. We take 10 people from that population. We get a distribution from that. We know that the mean of this is 27. We said that in the last video. The sample size is 10. And let's say that the standard deviation here is 3. I just made up that number. Let's roll with it and see what happens, okay? The next thing you have to do is go to your assumptions. So we're going to say, we'll assume this is normally distributed, right, with all these population parameters. But we're not going to assume that we know the population's standard deviation or variance. So I cross this out here. We don't know that. Okay, so let's go to the next step. And previously we would calculate a test statistic, but that test statistic here included this number that we didn't know, sigma. So we need to approximate that. So we're going to use the estimate of the standard error. And so we're going to use this formula, where we're going to use the standard deviation of the sample size over the square root of the population sample size. So the standard deviation of the sample over the square root of the sample size. Now, because we're doing this, we cannot use the z distribution we had previously used. So this distribution we can only use if we know sigma, but we don't. We don't know that. So instead we need to use a t distribution. So that will replace our z distribution, which we're not going to use. Now, if you remember, a t distribution is going to have fatter tails, and it's going to be a little bit shorter in the middle and fatter tails. So it's kind of like you squashed the z distribution down some. And also, the t distribution is a family of distributions. Each are differentiated by something called the degrees of freedom. And the degrees of freedom really is the sample size minus 1. So you'll have a t distribution for 9 degrees of freedom, 10 degrees of freedom, 20, 30. And the bigger the sample size you have, the closer you're going to get to this distribution here, the z distribution. And the smaller the sample size, the shorter this is going to get, and the fatter the tails are going to get. So our distribution in this case is going to be a t distribution with 9 degrees of freedom, right? Because we said our sample size was 10, so 10 minus 1 is 9. All right, next thing we do is make a decision rule. And we could use this same thing. Let's use alpha equals 5%, which means we only want to have a 5% chance of having a type 1 error, which means we want our cutoff values here to contain 5% in total, so that would be 2.5% here and 2.5% here. And if you remember these distributions, the t distribution, the z distributions, these are probability distributions, meaning that the area underneath here is 1 or 100%. And so if you take 5% off here and 5% off here, that leaves, 2.5 off here and 2.5 off here, that leaves 95% in the middle. So now the question we want to ask is how many standard errors away is this marker that we have here? That's what we need to look up on our t table. And so I happen to have a very nice colorful t table right here, and let's figure out what we want to do. So the first thing we know is our degrees of freedom. And we said that we had 9 degrees of freedom, right? Now, the way this table is laid out here, it tells us what the probability P is in this area. And if you remember from our drawing, we said that was 2.5% here, right? Never mind that we also have 2.5% over here. We just really want to know, what is this number over here? What is the standard error that gets us there, right? So we already picked the curve that we want. We want to use the distribution that has 9 degrees of freedom. And so here are the values for the ones that have 9 degrees of freedom. And now we want this upper tail probability. We said we want it to be 2.5. So we look for that. That's 25. That's way too high. 5. That's not even what we want. 2.5. There you go. That's what we want. 2.5. So we go down here, and we got this here, 2.262. So if we put our mean over here, we know that 2.262 standard errors here will give us 2.5% over here. And then on the other side, we're going to go in the opposite direction, so we're going to go negative 2.262, which is going to give us 2.5% in this tail. So this is the number that we're interested in here. So let's come back up over here, and we know the numbers that we're looking for here is 2.262 and negative 2.262. So if we calculate a test statistic that is greater than this number here, 2.262, then we would reject, or less than it, then we would reject. If it's in the middle, then we would accept our null hypothesis. Now, one point I'll make real quickly, it's a subtle point, but we'll make it anyway, is remember with our t-table, we had our number, our decision point being 1.96, not 2.262. That means that we have a lot less area in here than we do over here. I'm sorry, not area. We have a lot less space, between these two as you do between here. I mean, here you have about 3.8, whatever, 3.8, some about in there. Between these two, and here you have about 4.52 between here. What does that mean? It means that it's harder to reject the null hypothesis in this one because there's more space in here, meaning that when we calculate our test statistic, it's more likely to be in this area of acceptance than it is in this one because the target's bigger. Okay, let's calculate our test statistic now. So we'll use this here, and we know that, of course, this is going to be a little bit different, right? We don't know this, but we'll use our estimation. So we have 27 minus 30 over our thing, which was s over the square root of n, which equals negative 3 over, and s we said was 3 over the square root of 10. And so then we get this here, negative 3 over 3 divided by 3.16, which equals negative 3 over 0.94. Actually, let's make it 9.5 because that's really what it would be when you round it. And then this would work out to be negative 3.16. 3.16, so that's our number. So now, let's see where this falls on our distribution. Okay, so now in our distribution, it actually falls here, right? So negative 3.16 is the number that we came up with, and that falls within our rejection region. So again, we were still able to reject this null hypothesis. We don't think that it is 30 using the t-distribution and using our estimate of the standard error. Now, if you would want to calculate a p-value, we would have to find where on the curve, where on our distribution that 3.16 falls, and it falls somewhere between these two numbers, somewhere in there. And so we would say that, I don't know, our p-value is somewhere between 0.1 and 0.005, so maybe it's 0.007, 007. That's just an estimate. And also, let's say we wanted to do the confidence intervals here. So that was the formula we used previously, but now we have to make our substitutions. And so with our substitutions, we're going to put the t in here, and when we calculate this, we're going to use this formula here. The estimate of the standard error, the square root of, is going to be the standard deviation of the sample over the square root of our sample size. And I just plugged in the numbers again, 27 for this, 2.262 for this that we got from the table, and then 3 over the square root of 10, and that works out to 24.85 and 29.15. Once again, the number 30 does not fall in here, so this also rejects our null hypothesis. All right, this was kind of a lot, so if you have any questions, please go ahead and put a comment there or ask me so that I can try and clarify it a little bit better if you're not getting it. Thanks a lot. Talk to you later. Bye.